Hello everyone. We are going to talk about systems of equations in two variables. A system of equations is made up of two or more equations. For our purposes, these will be linear equations. A system of equations, the point of it is to find the solution to the system. The solution is all the ordered pairs that make both equations true. You can find the solution to a system of equations by graphing, substitution, or elimination. The first thing that we'll look at is graphing. In solving a system of equations using the graphical method, first you'll have your system of equations, and what we're looking at is just two equations. You need to graph both equations. If need be, rewrite the equations in the form that best suits you to graph. So what I chose to do is just to write it in slope-intercept form. Then you will graph both equations. Next, find where they intersect. This is the solution. So equation 1 I have written in red, and I have graphed it in red. Equation 2 I have written in blue, and I have graphed in blue. Where they intersect, and it occurs at the coordinate 3, -5, is the solution to the system. I can visualize this graphically. Now sometimes graphing isn't the best method to use, though you can look at it and say, okay, that's pretty simple. I know how to graph this equation and this equation, and man, all I got to do is find where they intersect. But sometimes the equations that we have, y-intercepts can be so far apart. It's the scale that we must graph on, and then to be able to find where it is. My point could be all the way far away from the origin. So sometimes they can be difficult to use graphing. So what I've shown over here is that we can also prove it algebraically. With this, in this case, I know my point, 3, -5. 3 represents the x value, -5 represents the y value. I take those values and I plug it into the equation, and I solve and see if I end up with a true statement. I ended up with a -5 equals a -5. That is a true statement. Therefore, that coordinate is a solution to equation 1. Then I must do the same for equation 2. I plug in a 3 and a -5 for the corresponding x and y value, and I solve. Again, I end up with the true statement. -5 equals -5. I have verified that this is the solution. But again, I want to go back to the fact that sometimes graphing is not practical due to the scale of the graph that you will have to have. That you would have to use the substitution method or elimination method to be able to solve. And those can be just as quick. So in our example, we saw that there was a solution. But as we pointed out before, the solution is all the ordered pairs. So you can have more than one point, or you can have no point or coordinate as a solution. But most graphs intersect at a single point whenever you look at it graphically. There will be one coordinate as your solution. But there can also be no point of intersection, and what this means is no solution. Or there can be infinitely many solutions. And to visualize this graphically, one solution, they intersect. We say that is consistent independent. Consistent meaning at least one solution. Dependent meaning if one equation can be obtained from the other by multiplying by a constant. That was one solution. No solution. No solution is simply parallel lines. Parallel lines are equidistant apart. They'll never intersect. Whenever you have parallel lines, we call that inconsistent independent. For infinitely many solutions, notice I have been using red and blue. So what I did was I used purple to illustrate this line. That is because it is the red and the blue line. They end up being the same lines. These are identical or same lines, and we call those consistent dependent. For this line, to show you an example, let's say I have something like this. I have y equals 2x plus 1. And then for my second line, I have, and I'll just write it out with everything, 2y equals 4x plus 2. What I've done is and we'll call this equation 1, and we'll call this equation 2. And again, this is going back to where I'm talking about infinitely many and dependent equations. Equation 2 can be attained from equation 1, simply saying, well, if I multiply equation 2 or equation 1 by 2, I end up with this. Or I could say vice versa. Equation 1 can be attained by equation 2 if I divide everything by 2. That is what is meant by dependence. And this right here goes back to something that you've already been doing. These are the same line. You can say that equation 2 is scaled up by a factor of 2, or equation 1 is scaled down by 1/2. But we've already dealt with this when we deal with fractions. If I have the fraction, and we'll pick an easy one, how about 1/2? I can say 1/2 is equal to 50 over 100. Both of them mean 1/2. It's the same with this. What I've done is I have taken 1/2 and I have multiplied it, numerator and denominator, by 50. They are still the same value. If I worked it out as a decimal, these two equations are still the same equation. They are dependent. Whenever they're independent, it means that there are two separate equations. One cannot be obtained from the other. Whenever they're consistent, they have at least one solution. Inconsistent, they do not have a solution. And you'll have homework problems that ask you about consistency and dependency. I also would like to point out that parallel lines have the same slope. So there are certain things with your system equation that you can look at before you even start to solve to say, oh, I see that this equation is a form of this equation, or I see that they have the same slopes. So in graphing and finding your solutions graphically, one solution, no solution, infinitely many. And you will have this same type of solution set, one solution, no solution, infinite many, whenever you solve using substitution and elimination. Please watch the publisher's videos, critically think and structure your homework, and good luck on your homework.